Hey everyone, I'm Fernando. Welcome back to the channel. In today's video, we're going to be talking about one of the hottest topics in modern application development, that is microservices architecture. Whether you're just getting started or you're looking to refine your current microservice architecture, stick around as we cover the essential best practices that'll help you define an efficient and scalable system. So first off, what is a microservice architecture? It is essentially a evolved design pattern that involves building your application in collection of loosely coupled components, essentially. These components or services interact over lightweight and well-defined APIs, which act as contracts between different services. Think of it as breaking down a large, very complex monolith into each individual piece that makes sense to be alone and isolated from the rest. This approach allows you to create very scalable and efficient systems that are much easier to maintain and to grow as well. And by using these patterns, by using microservices, you're usually gaining three major benefits to your overall architecture. You get faster development and delivery times because each individual microservice can be worked on in parallel by different teams. So essentially, instead of having just one big team that needs to coordinate all the different moving parts, you can actually have isolated teams working each one on their own specific track, allowing them to move in parallel as long as there is enough coordination, communication between each other whenever it's required. You get better maintainability because, again, the code base is smaller. Not only that, but you also gain the ability to use the best tech for each individual service. Remember that these services will interact with each other through a standard API. This standard API is usually technology agnostic, which means that each service could be developed using different frameworks and even different languages. And because of this flexibility, each one can be developed using the best technology for each use case, in particular for each microservice. This way, you get smaller code bases, which are easier to test, easier to maintain, and you get the best in-class technology for each one, which also improves the maintainability and the overall coding experience for each team. And finally, the last benefit that you get from microservices, which I think is the best one, is scalability. Scaling microservices is much easier than scaling a whole monolith together, because this is because usually microservices tend to be stateless. This is not always the case, but when they are, all you have to do to scale the service is just create different copies of it, whether either inside the same server to really take advantage of all the processing power or the memory of the server, or just create different copies of the server and put them all behind a load balancer. Because they are stateless, traffic and user requests can just be iterated over different copies of the same service, and the overall user experiences remain the same. So this way, you don't have to rely on really resource-intensive hardware, which tends to be on the expensive side. With these type of services that are stateless, that can be very easily scaled up, you can use commodity hardware or relatively cheap hardware that can run these services, which are, remember, each service is isolated and only focused on a single domain of functionalities, which means they are just a part of the whole system. That means they require less memory, less processing power, and everything regarding resources will be reduced as compared to the entire system. So that way, using these services becomes cheaper, a lot easier to scale up, and you can also scale down whenever needed, which means you gain cost efficiency through these patterns. Now, let's look at some of the best practices when it comes to creating your own architecture around microservices. So the first one is probably one of the most important ones when it comes to defining the architecture and defining the limits of each microservice. And I kind of hinted at already during the previous section, but this is the single responsibility principle for microservices. What it means is that each microservice should only have a single responsibility. That doesn't really mean that the microservice should only have one functionality or one endpoint. What it means is that it should only take care of one thing, right? Sometimes microservices are separated around resources. For example, you have your users microservices, you have your product microservices, your shopping cart microservice, and so on. So each type of resource will have their own microservice. That microservice will essentially hold all the functionalities that your system requires around that resource. Another way to do this is using domain-driven design. You can actually define bounding context around the different business needs of your product and then separate that monolithic idea of an application into individual microservices. There are many ways in which you can achieve this, but the point is, at the end result should be microservices that only handle a single responsibility. How you define that responsibility is up to you and your specific context, but keep that in mind. And here we're seeing an example of that same concept. For example, you have this e-commerce site. For it, you could have the product service, the order service, the payment service, and so on and so forth, essentially. Each individual microservice is responsible for their own tasks, for their own domain. And that makes the overall system modular and more scalable, easier to maintain, and everything else that we've been talking about so far. Another best practice is actually around the teams and not necessarily around the technology. Like I said before, one of the benefits that you get from these individual microservices is that each one can be developed by an individual team. That is not always the case. It depends on the size of the project, the size of the company, the amount of people working on it. But sometimes a single team will handle several microservices. But the point is that you get this flexibility around how you structure your teams. Now, usually what happens is companies will structure teams around responsibilities or around roles. So you have your UI UX team, the backend team, the front-end team, and so on, right? When that happens, a single service or a single product will have to go through the entire roster of teams, essentially. It will force all teams to coordinate and try to organize their timelines and the set of tasks, the priorities even, to get them to work on the same functionality, on the same service in this context, and release everything on time. Now, instead of doing that, what you could do, given the flexibility that microservices give you, is to structure your teams around your microservices and have these teams be cross-functional, meaning that for each team working on a single or multiple microservices, you will have someone from UI, UX, someone from front-end, someone from back-end, someone from database, and so on. So that way, coordination is done within the team, and each team has their own timeline, their own goals and milestones that they have to hit within the roadmap, and there is no need to have different teams coordinating with each other. Each team is encapsulated and a self-sufficient unit of work. Another best practice around your microservices is making sure that you're using the best tool for each job. And when I say tool, it can be a tool per se, essentially something that for CI/CD, for example, or a compiler, or it can be the framework that you use or the language that you use. This is all going back to the point of each microservice being an individual unit that can be developed in isolation from the rest. As long as the public API is known by the other microservices, the way you implement it and work with it, it doesn't really affect the others. So there is no need to have a company-wide standard forcing every team working on these individual microservices to pick a set of tools, to pick the same framework or the same language if it doesn't really make sense for that use case. Again, this is about using the right tool for the right job. Some examples of these tools that you might want to look at are like Jenkins and Bamboo for deployment automation, Docker for containerizations, obviously, Postman for API testing or definition, Kubernetes for container management is also a great idea. Using, for example, Logstash for centralizing logs, which in this case of microservices, trying to understand where each microservice is storing the logs and what information is there is going to be really a problem that you need to solve. So using something like Logstash, or even the entire Elastic Kibana and Logstash combo is really a great idea to not only centralize but also search and display results or analytics that you want to get out of those logs. Following DevSecOps, for example, to manage your entire software development lifecycle is a great idea. When it comes to version control, obviously GitHub is one of the best options out there. There are alternatives. It depends on your context specifically. If you can use something like GitHub that adds a lot more around Git, you should definitely try that out. Something like Amazon SQS, the simple queuing system that allows your microservices to interact with each other, is definitely a fantastic pattern. It allows for reactive architectures to be developed. And the SQS is a very scalable solution. There are alternatives as well, such as Kafka and other that you can deploy even on-prem, and you don't need public cloud providers for. But definitely something managed like SQS is a great first step. Now, when it comes to development, checking the quality of your code and everything else around your code, something like SonarQube is a great tool, something that you should look into when it comes to defining the entire architecture, which is going to be something, again, that you will need to take care of. Right now, this is no longer a monolithic approach that we're taking. We're talking about deploying a distributed architecture that can have multiple servers in different places, different configurations and different resource requirements. Using something like infrastructure as code, Ansible will be for this a great option. And finally, any project requires issue tracking, and Jira, even though a lot of developers tend to hate on it, is a fantastic tool, especially when the project is big enough and the team is big enough. And we're talking about microservices here, where the potential to have tons of them is big, and each one having their own team could require something a little bit more complex when it comes to project management than something like Trello. So Jira in this case is a fantastic tool that has everything that you will ever need. Best practice number 4. Use asynchronous communication. Now, one of the biggest problems that you will have to decide on and solve immediately when you start designing your architecture around microservices is how they're going to interact with each other. Because let's face it, these microservices are not here to just directly communicate with the front end of your application. Some of them will only interact with each other, so systems talking to systems. Now, the easiest way or the more straightforward way is to just communicate them directly, either using sockets or using something like HTTP, which is a very standard method of communication. You can just get them to communicate with each other. Essentially, which is the example that we're seeing here right now. Each service is going to communicate with the next one in a serial way. So when, and this is the downside to this approach, when the request from the user comes, the amount of time that it will take for that user to get a response back is going to be the addition of each individual service doing their work and then sending the response back. And on top of that, you can also add a little bit of latency due to just the protocol HTTP, which adds a little bit of time with the communication. You could improve on this by using sockets, which would allow the connection to stay open and have a more dynamic communication, or at least a little bit faster, but it would still remain serial. And the problem here is that when the system is complex enough and when there is a big enough number of microservices in the backend involved in a single request, then that request is going to be it's going to just take way too long for the user to get the response, and that will affect directly the user experience. What we're trying to avoid here is for the user experience to be affected by our architectural decisions. How do we solve that? Through asynchronous communication. And I kind of hinted at in the previous point, but if you have a centralized message queue, be it SQS, Kafka, or something else that you want to use, the point here is that you need a message queue between all of the microservices, and then suddenly your communication becomes an event-driven architecture. So instead of having one microservice sending a specific HTTP request to the next one, you just have all microservices sending and subscribing to events inside the message queue. And now suddenly one event from a single microservice could be picked up by 2 or 3, as many as you need, microservices that can work in parallel to solve part of the request and then send back the response. In the end, you will have to understand, how much you can parallelize that and how much it can't be parallelized. But the point is that you gain speed, because now you suddenly are able to send back a response immediately to the user saying, your request is being processed, just will notify you when it's ready, and the user can go back to browsing your website or using your application. Essentially, the UI is no longer locked, waiting for a response. Granted, they don't have the response they wanted immediately, but at least they're able to keep using the application. Eventually, when the response is ready, they will get a notification back through the exact same method, and they'll be able to get that whatever they were looking for. Now, the other huge advantage that we get is that we decouple the microservices from each other. If you rely on a direct microservice to microservice communication, if you have A and B, or in this case, for example, the CAT service requiring to send a message to the delivery address service, the CAT service needs to know exactly where the delivery address service is located. That is, which server, which IP, which port, and that needs to be somewhere. That configuration needs to be stored somewhere, either on the code, which we don't want to, or configuration files, secrets, whatever. But it has to be there somewhere so that the microservice can use it. If tomorrow, for some reason, we change our architecture or we just redeploy delivery address service somewhere else, and we forgot to update that configuration, then our system is going to break. It's definitely not a huge problem and something that is very easy to solve, but it's a point of failure that we can just avoid by decoupling them from each other. There are other alternatives to do this as well, but through the message queue, you also gain the reactive nature, which I think is the best solution for microservices, because it's definitely a great way to gain speed and improve the performance of the UI through very well thought out architecture in the backend. Now, the best practice number 5 is adopting DevSecOps for security, essentially. When it comes to inter-service communication, when it comes to essentially a microservice-based architecture, which has so many moving parts, because remember, each microservice will have access to a database, for example, or will have to know information about secrets or external APIs. There's a lot of secret information or secret data that will be distributed. So this is where security, and specifically DevSecOps, comes into play to kind of organize and solve that problem that you will get if you don't really take care of it properly. This process, essentially, this methodology allows you to integrate security into the CI/CD pipelines. So it checks your code, it adds on top of your code so that you don't send hard-coded credentials, for example, into production, so that you don't add security holes in the system through code. Now, through the implementation of DevSecOps, you get high security assurance, because security is integrated, again, throughout the entire development process. It reduces the chances of you pushing a vulnerability undetected and untested, essentially. It also reduces the code vulnerability as a whole. The automated checks that are performed on your code on top of the unit test that you would add allow you to identify and fix known flaws on your system. You get an intrinsic enhanced quality in your product because this continuous testing and monitoring allows you to push features that are more secure and less error prone, essentially. All type of errors or problems that you will push because of security vulnerabilities are no longer a possibility. You definitely gain productivity in your development because there is a lot of testing and checking that is done automatically when as part of the software development lifecycle. That means that you don't have to manually check, or someone else doesn't really have to manually go through your code or check for vulnerabilities. They are all automatically checked every time you push code. And finally, again, you end up delivering better and more quality software much faster. As the conclusion of everything that I've been saying, essentially you get through these automated tests as part of the CI/CD pipelines, you get a focus on security that allows you to just push your code knowing that if it's safe, it'll go into production. If it's not, you know that there is a gate that won't let it pass. Best practice number 6, and this one, take it with a grain of salt, but essentially you should use a separate data store for each microservice. And this one is a little bit controversial. In theory, each microservice should have their own database. That said, and as we're seeing here in this diagram, you can have different services using different databases, and in one of them having a reference to the other. The problem here happens when this data needs to be joined. These tables that are in completely different databases need to be joined either for a feature of your product or perhaps due to reporting requirements. Now, there are ways to solve this. You can, if it's reporting, you can definitely have a process that normalizes everything and just extracts the information, puts it all from the different databases into a single one for reporting needs. So without actually affecting the performance of the production databases. But if there are some cases where the data design, the data structure design is not that ideal, or even the separation of concerns between microservices is not well thought out. So in the end, that translates to a data model that is not fully decoupled. And when that happens, you end up actually sharing a single database between multiple microservices with the intention of optimizing the way in which they interact with the data, because otherwise you end up having to add extra code and extra logic to pull data from different databases and then showing it or do whatever operation you need to with it. The thing that you want to avoid is just keeping duplicated data for the sake of improving efficiency and keeping each individual microservice with their own database. If you do this, now you have a duplicated piece of information that needs to be updated every time in both places. You essentially made your job a lot harder to maintain. Your logic now needs to maintain the data in both places. This is something that you don't want to do. So again, take this best practice with a grain of salt. You should be aiming as a rule of thumb to have a single database per microservice. If that's not the case, then make sure that that's not the case because of an actual valid reason and not because of a flaw in your design, which drills down to a flaw in or a poorly designed data model. Now, best practice number 7, and that is something that usually happens automatically: deploy your microservices individually. So one advantage that you get immediately from the process of splitting your architecture into multiple microservices is that each one can be, again, developed individually, and because of that, they're essentially an individual project that can have or should have their own individual set of CI/CD pipelines and deployment processes altogether. If you want to update a single service, a single line in a single service, it doesn't really make sense to deploy the whole architecture because of that change, which is something that would happen if you had a monolithic architecture, right? You would have to deploy the whole thing, even though the change that you made is very small in a specific section of the platform. But because you have every microservice isolated into their own project, doing this and configuring your deployment processes to work on individual cases should be relatively easy. Usually what you do is you have these microservices, all the code for them stored in different repositories. And from there, you create the pipelines for each one individually. Best practice number 8, orchestrate your microservices. Orchestration can mean many things, and depending on what or in which environment you're deploying your whole architecture, it can be done one way or the other. But the whole point of this is that these microservices will create a problem for you once the number of them is big enough. If you have 1, 2, 3 microservices, that's not a problem. You can just even deploy them manually. You don't really care about it. But big systems will have 20, 30, 100 microservices. And when that happens, and each one needs to be scaled up, down, have their own rules around how resources are managed, then you can't be bothered doing that manually. Otherwise, you just become the bottleneck. And that's where orchestration comes into play. Tools like Kubernetes, AKS or Azure Kubernetes Services, ECS, meaning Amazon Elastic Container Services, Azure Containers App. Essentially, everything around containers should help you orchestrate that chaos that will be your architecture, your microservice architecture. And I don't say chaos in a bad way, but it's true that many companies will fall for the trap of thinking that they don't need orchestration. They can manually configure and monitor and just deploy their microservices without a problem. The thing that they don't see is that when the architecture grows big enough, then you need automation. You need orchestration in that place. That will allow you to grow and scale to the next level, which is having that dynamic flexibility, that scaling up or down and being more cost efficient, especially if you're in the cloud or using limited resources. You want to be efficient in the way you use those resources to make sure that you can handle the traffic that you receive. The final best practice is to remember that you have to monitor your systems. Again, if you have 1, 2, 3 microservices, this is not going to be a huge issue. You can set up something very easy and monitor the resource utilization, disk utilization, and performance of your microservices, how many requests they're receiving, how many responses per second they're able to send back. That's not a big issue. The problem here, and this is why you need it, is when the architecture scales. When you need multiple instances of each individual microservice, when you have so many microservices that you don't really remember how many you had. And this is not really a strange use case. Many big companies have this quote-unquote problem when their microservice architecture grows big enough. Now, because of this, there are a lot of solutions that will do the monitoring for you. So it's really not a huge problem. You just need to remember to have that implement. Something like AWS CloudWatch, Jaeger, Prometheus. These are all some cloud-based, some open source solutions that you can set up and have your entire architecture monitored in minutes. And you centralize all that information and you're able to act on that information, whether it's triggering scaling rules or notifying your developers because there is something wrong. But the point is you are aware of what's happening with your ecosystem of microservices, which is something that you definitely need to be aware of. Otherwise, your application could be failing, even if you have, especially if you have a reactive architecture, because in those situations, the asynchronous nature of that communication prevents common errors, common problems. Just return a 500 error to the user, and that's not how you want to be notified, but at least that would be very obvious to you or whoever is using the application. In some situations, your microservices might be failing, and those errors might just be logged in some godforsaken log file that no one's monitoring, no one's even ingesting. So your user might not be aware of a problem that is just hidden within the architecture. So through monitoring, you can pick up on those problems. You can pick up on slow response times, on errors that no one's looking at, and you can act accordingly. So remember, monitor your architecture. And there you have it. Those are some of the best practices when it comes to defining your own microservices architecture that allows for a scalable, efficient, and stable platform to be developed. Be sure to like, share, and subscribe to the channel for more content like this in the future. Until then, see you in the next video. Bye.